we now have a pretty good both experimental and theoretical understanding of how it is that the quantum becomes classical, and why in doing so certain properties become real, if you like. They become measurable. They become things like mass and charge and so on can be measurable, but some other things don't. So there's no macroscopic equivalent of quantum spin, for example.
Right. And so you use that to explain, you mentioned the theory of measurement, and this I thought was extremely subtle and interesting, so I hope you could say more about it, that at the level of the quantum, when you do a measurement, and you think of the measurement in a sense, in the book, you argue it's a kind of information transfer, or almost you could say an information subtraction, because it has as a corollary at the level of specificity that you're describing, which is highly technical. The information, once it's out of the sort of system, is no longer sort of in the system. And that's part of this process. Is that correct? And that's related to the way measurement is sort of, or the way decoherence is sort of, like you mentioned, giving us maybe a much more technical and precise almost account of what measurement is and what it's doing with respect to why then is we can push towards this, because you then use this to connect to computing and like more and more reasons to think, look, what's really going on here is about information theory. It's about how information and communication works. And that's connected to the decoherence and the way decoherence is telling us sort of what's going on in measurement.
Yeah, well, I think thinking about it in terms of information, to me, it helps to sort of make sense of what it is that's going on. I mean, in a sense, it looks as though information is being lost when we go from quantum to classical. If we think about, for example, one of these systems that is in a superposition, either up or down. So there are two possibilities there, and both of them could be realized. But when we make the measurement, we only find one of them. And we don't know which one it's going to be, but we know it's going to be either one or the other. It's going to be either up or down. So what happened to the other one? The other one was a real possibility. Quantum mechanics has it in there in the Schrödinger equation, but now it's not a possibility anymore. It's gone. We've only got, one answer. So in a sense, there does seem to be a loss of information there. And that's in quantum mechanics, that's there's a sort of technical term for it, that it's called non-unitarity. So and this is kind of the remaining puzzle about quantum mechanics, where that information goes, where that other information goes.
This is connected to the wave function collapse. Is that right?
Yeah, that's right. Now, what if we think about this sort of new understanding of measurement in terms of decoherence and so on? Actually, there's nothing in there that destroys that information. All we're saying is it's getting more and more spread by interactions with the environment, and it sort of goes everywhere, and so it's virtually impossible to collect enough, to look at enough sort of parts of the system to reconstruct where that information is. But in principle, it's still there. In principle, we could undo. If we could imagine undoing all of those interactions, it's a bit like undoing the trajectories of particles in an ink droplet, and tracing it and reconstructing the original droplet. It will be that difficult to actually do it, but in principle you could, and in principle you can undo decoherence, and this is actually called recoherence. And in some simple situations where you've only got you can control the system so that you've only got a manageable number of interactions, recoherence has actually been shown experimentally, so that you can almost rebuild your superposition. So we know that that's possible. So what the theory doesn't answer is what happens to that information that seems to disappear. What happens to those other states that we know could have been there because they're in the wave function, but that once we made the measurement, that's it. You can't see them anymore. And that's really the remaining the remaining challenge for quantum mechanics. Why, in a sense, what it's asking is, why are things unique? That quantum mechanics doesn't have an explanation for. We can explain why things look classical and why we can measure them, but we can't explain why we only see one of the outcomes and not two classical objects somehow in some kind of space that both exist. And of course, there is the interpretation of quantum mechanics, the many worlds interpretation, which says, absolutely, we do. Both of those do exist. They just exist in different worlds, in some sense, different universes that no longer interact. And, so that any sort of one of us only sees one or the other. And that's, that's a possibility. It's certainly a possibility that gets around this apparent problem of loss of information, of non-unitarity. But to my mind, it raises a whole host of other, sometimes they might be philosophical problems, but I think they're nevertheless real problems. And some people think, well, maybe we just have to put uniqueness in by hand as an axiom. Maybe, the way to think about the universe is, well, it behaves like quantum mechanics tells us, plus there's only one of them. And, in a sense, that's all you need. If you have those ingredients, then you're fine. But it does mean you've got to add that assumption of uniqueness in. But maybe that's, some people would say, well, what other assumption could be better empirically founded than uniqueness? When have we ever seen anything other than a single reality? So, surely that's a reasonable thing to add in. But, others say, well, nevertheless, there's no fundamental justification for it. It's still an additional axiom. So this is where the arguments are. And the whole issue of collapse of the wave function, to my mind, that's an outdated and no longer useful way of thinking about the problem. It seemed that term was sort of coined when we didn't really understand measurement at all, and it seemed like this magical thing happened to turn quantum into classical by the whole wave function somehow collapsing. Now we have ideas like decoherence that can explain all of that process of quantum going to classical, except for uniqueness. So instead of collapse of the wave function, we should be really talking about the problem of uniqueness.
And uniqueness here meaning specifically why, say I have two states that are possible, like an up or down position, why you will get the one that you get.
No, just that why you will get only one. It's very hard to think about, what would happen otherwise. How could you sort of get them both? But that's in a sense, that's a problem for us trying to think about how we are in the world. What would perception be if you could have both of these states? We don't know. But as far as quantum mechanics is concerned, there's no obvious reason why you shouldn't. When you make a measurement, somehow get two classical objects out of the two possibilities that were already in there. So the question of why we see one or the other, as far as we can tell, that's completely random. And even in the many worlds idea, it's completely random whether a version of us will see an up or a down, because the other version of us will see the other. It's in that in that sort of elision, I think, that the problems arise, because then you have to sort of say, well, what do you mean by whether we will see up or we is both of us, get into those problems. But that question of which we will see does seem to be fundamentally random, and in a sense, why not? Why should we expect it to be otherwise? But the question is more simple. It's just why just one and not both.
Right. So why not sort of a full actualization of the apparent full potential?
Yeah, exactly. Because that's all in the Schrodinger equation. All those possibilities seem to be in there. So what happens to the ones that don't seem to be actualized? And that that's not just a sort of philosophical question. It's there's a technical way of expressing it, which is about loss of information, and that isn't really explained.
And that's part of the concern, is that you could have an apparent loss of information when there's no sort of explanation for why it should be lost. And indeed, now we can see through decoherence, it's like, no, the information's out there, it's just not in the it's spread out, so the whole can't be seen. It's even though the part can't be interpreted by itself as a part anymore. In theory, if we could see the whole, we could reconstitute the relevant information to understand that transition. But that's sort of the faith, I guess, or the uniqueness bothers that faith, that there could be somehow apparently all of this information, But then once you have a measurement, you get only some of the information, and you can't. It seems like the frustration is what happened to the remainder.
Yeah, and it's that apparent disappearance of information that connects this idea of measurement or collapse of the wave function, if you want to think about it in those terms, to the directionality of time. Because that's the irreversible step. And like I say, if you just think in terms of decoherence, nothing about that is in principle irreversible. It's just very, very hard, practically impossible to do, but in principle it could be done. So it seems that when it's in losing that other information that quantum mechanics suddenly seems to become irreversible. And there are, I mean, that really, it really is sort of mysterious, because it does seem to suggest, and Lee Smolin, the physicist in Canada, has made this sort of proposal that that's really how we should think about the distinction between the past and the present and the future. We make that the past is the past only becomes the past when it can't be undone, right? When it's happened, when we can say this happened, and there's no going back on that. I mean, the strange thing in some quantum experiments is that we seem to be able to get into a situation where it seems that something has happened, but we still have a kind of potential, it seems, to go. There's a kind of a fuzziness about the outcome, and we have the potential, while that fuzziness exists, to go back and actually change the outcome, so that it crystallizes out in a different way. And this is sometimes it's talked about as retro-causality. There are some quantum experiments that some people think are best understood, or best discussed, perhaps we should say, in those sorts of terms of, you've sort of made a measurement, but you haven't quite crystallized it enough that it becomes irreversible. You can still go back and seemingly, or you can still do something that within that sort of fuzziness in space-time seems to have a retro-causal effect, so that actually, a different thing actually crystallizes out in the end. And I think this is a really sort of exciting and fundamental aspect that's sort of now coming out of quantum mechanics, of how it ties in with things like the second law of thermodynamics, which is all about reversibility and irreversibility. So some people are really thinking, what does quantum mechanics, what does collapse have to say about the second law of thermodynamics? And is there some way of maybe circumventing it by exploiting this this sort of zone of uncertainty that can exist in some quantum systems before the measurement has become definite?
Oh, so that's absolutely fascinating. I wonder if you'd say any more about the connection between the time, this issue you brought up, and the laws of thermodynamics. I thought of that when you mentioned superconductivity as an example of sort of some of the technical applications, that sort of, just like it was very surprising in sort of, I read a book, or was reading a book, I forgot the physicist's name. I think he was the first physicist in England who got froze liquid helium, but he wrote a book called The Search for Absolute Zero, Kurt Mendelsohn. But he was talking about sort of the surprise, obviously, that emerged when we started to converge towards near zero. Kelvin and the superconductive phenomena and stuff like that. And I was very just struck, about the implication of quantum mechanics as a fundamental theory of physics. Being a theory of information then does have a quite direct connection, even if it has to be spelled out or figured out in the science, between sort of what we think about maybe information and what's going on in our assumptions about thermodynamic systems, right? Because there does seem to be these strange corollaries. Like in certain states, you'll get a transformation of the system so that the information is entangled, in a sense, which you could see in one sense as one thing disappearing and another thing appearing with two sort of spatially distinct properties, which is another way to me that I thought is very interesting. It's as if when you're doing this level of physical analysis, it's as if you're having to watch time in motion and account for it in some sense. In other words, right, because the classical assumption in the assumption is Spinozistic, right? It's the principle of sufficient reason. Everything has an explanation. That's sort of the principle that Kant also tries to restrict to only science. He thinks it destroys human freedom, but Kant defines science by the fact that it deals with universal and necessary principles. And it's the conjunct of universality of a phenomenon or a principle and its necessity that constituted scientific status, which is a very, I think, deep intuition still in modern physics, which makes sense. So simplifying things lets you explain more and more apparent discrete phenomena under fewer or more powerful, ultimately, principles. And then the problem of quantum uniqueness, I guess, is that it seems to sort of get in the way of that project and almost imply a reversal of it. That no, maybe actually the assumption we had based on classical mechanics that things were sort of fundamentally, once we understood something, we'd understand it sort of in toto or universally. Maybe it's actually at root, like you're saying, it's about contingency. That is very exciting. It does seem to get us towards a different issue about even what the theory is saying about how we think about, you know, energy, if that's energy and time. Space and time are the most fundamental things. So space, time, and energy then seems like that's what you're discussing. The way it implicates what Kant would call the forms of intuition, the concept of space, the concept of temporality itself, which is connected to, you know, spontaneity, which is sort of his fundamental category, just the fact of emergence. Things are happening, not just living things, but somehow things are happening. And Kant thought you can't explain that, but you have to assume it, at least in living systems. But in quantum mechanics, seems almost as if spontaneity is emerging inside of sort of the most rigorous mathematicized fundamental physics. And it's creating all of this excitement.
Well, I mean, there's certainly spontaneity, as far as we can tell. There's certainly spontaneity in the sense that there is this irreducible randomness in quantum systems. And, you know, again, there are some people who think we're going to get underneath that and get rid of that randomness because we don't like the idea that things will just, you know, go this way or that way with no apparent cause. You know, that was the problem that really sort of rose up in the early days of quantum mechanics. And Heisenberg said, you know, it seems to spell the doom of, you know, notions of causality because things happen without a cause. That, you know, to take an example, a radioactive atom decaying, that's a quantum process ultimately. And what quantum mechanics seems to tell us is that it will just happen at some point. And, you know, there are properties of that atom that determine the probability of it happening, you know, after an hour or a day or a year or so on. But there's, you know, that's all it can tell you. It can't tell you when it's going to happen. That decay is acausal, you know, and that just seems to be fundamentally the case as far as we can tell. But the question of information, I mean, you know, I think that these are the ones that are really sort of really exciting in that they are suggesting connections between the way we understand quantum mechanics and other areas, other fundamental areas of physics. And thermodynamics is one of them. This question of how quantum mechanics and how the notion of information in quantum mechanics connects to the second law of thermodynamics, because, you know, information was also at the heart of the conundrum of Maxwell's demon, this little creature that could, you know, seemingly defy the second law of thermodynamics classically by using information about the microscopic, you know, environment, about the particles it sees, to sort of separate hot from cold or create order from disorder, really. And the whole, you know, that argument sort of fell on the question of, well, there are problems with how you collect and deal with and store the information required to do that. It's so, you know, the flaw in Maxwell's demon is an informational one. And it seems that, you know, people are now working on quantum Maxwell demons where, you know, there are different questions there because of the different nature of what information does in quantum mechanics. There are different questions about, you know, how a quantum Maxwell demon would work and what its constraints might be, and more broadly how quantum mechanics and thermodynamics in physics, and in particular black hole information paradox. So the idea that it seems black holes, it looked as though objects falling into black holes, I mean, if you can literally think of a hard drive falling into a black hole and you can never get it out again. That's the sort of typical way of looking at it. That information is like there's a non-conservation of energy there somehow. And then the whole discussion was about, once Stephen Hawking showed that actually black holes can evaporate, so not eternal things, they can disappear again. What happens to the information that they might have swallowed? Can you get it back again? That's been a big debate rumbling on for the past 2 decades. And now there is, I think, a pretty good understanding, and I think almost pretty much a consensus about the fact that you can get that information back out, and that information can be recovered from the evaporation of the black hole. That essentially the information is kind of evaporated out, is broadcast back out, and there are all sorts of questions about how you can get it and how quickly it comes out. So it's really striking that, in both of those instances about general relativity and thermodynamics and how they connect to quantum mechanics, it comes down to a question of where is the information and what happens to it and what can be done with information. Is it a conserved quantity? And if it isn't, what does that mean? Where does that go? And because we know that there is a relationship between information and energy, what does that imply for thermodynamics if information can be destroyed? So, the quantum mechanics is now sort of connecting with other areas of physics in a way that is, I think, just starting to suggest perhaps a sort of general framework that seems to be information based for thinking about what is and what isn't possible in the universe. And there was something I was going to say about that came that related also to the question that we were talking about earlier about information. It's going to come back to me. It flitted across my mind. Maybe we'll get back.
No, it's fine. It could have been connected. You had mentioned, I don't know, superconductivity was connected, but I'm not sure if it's one of the thermodynamic or the things.
No.
Let me ask you this. Well, first, just to be clear, would it be fair then, based on what you were maybe implicitly drawing, that you could see a kind of almost a very distant but intriguing analogy between this emerging consensus about, in fact, being able to get the information back from a sort of a black hole that's apparently disappeared entirely, and something like recoherence?
I think as far as I'm aware, I'm not aware of any fundamental. It sounds like the two are similar. I'm not aware of any fundamental connection between the two, because other
than the information, I guess, analogy.
It
seems like, in other words, if you, not as physical problems, obviously, and I would be incompetent anyway at both of the areas, but I mean, the level of analogy, I guess, I thought was intriguing at the level of, if you thought of, say, information theory as its own science, then the phenomenon of apparent information loss and its incredibly worrying implications for potential, energy cannot, right, obviously shouldn't be able to be lost. And if information's lost, then presumably somehow maybe energy is being lost too. And that seems very problematic at a fundamental theoretical sort of principial level. So, well, where are some cases of really interesting apparent information loss that's very worrisome? Well, it turns out in the former, badly described, yet say wave function collapse, but we can now describe through contextual, the contextual aspect of quantum mechanics and decoherence. That's one example. That's obviously its own thing. But then it is interesting that, well, apparently here's another example. What if you did stick? What happens to the information that goes into a black hole? And again, I'm not saying there, but it's just interesting at the level. This is part of what I find very suggestive about the utility of information philosophy or information science, is it creates a kind of a third space of conceptualization that allows you to conceptualize aspects of problems as having a unitary component, even though their current division in the highly specialized different areas that they exist in physics may not yet manifest any such connection. But if there is some connection, just to say, hey, well, let's at least think about these as two instances, both extremely interesting in their own right, one from sort of cosmology and another from quantum mechanics, two instances of a problem of information loss recovery and maybe a reversal of information loss. I don't know. It seems like because that would be seemingly also connected to the time issue. If what you interpret as the determinacy of the past to mean a kind of information closure. In other words, the past is determined because we can't add information to it. The system is no longer sort of receiving input. And the input that we have relative to it must in some sense be asymmetrical in its sort of determination, that we're somehow being affected by it, but we're not directly affecting it. That's at least seem, right? That'd be an information way of describing like history. But then, it's extremely interesting to just think about, well, what if it is possible in some very narrow context to take a state of full potentiality, say in a superposition, and then actualize it or determine it, but then be able to, under those highly constrained conditions, return to the superposition. I don't know. It does seem to, I don't know what it implies, but it does seem to have remarkable potential implications for just what we think information does or can do.
I think I can see certainly what you're driving at, Samuel. I think it is true that at the root of both of those problems that we talked about is this question of reversibility and irreversibility, which is obviously where time comes in. It's really a question about, can we, I suppose it's a question of when can we say something happened? And if it's reversible, fully reversible, not just that you can sort of pick up your glass and put it upright again after you've spilt it, but actually fully reversible so that you can return it to the original state, then we can't say a thing has happened. I do think that in both of those cases, there does seem to be something very fundamental about the way we understand. It's almost as though, it's not even so much about time as some abstract thing, as about, when, as Lee Smolin says, when the present becomes the past, when things become fixed, when you can, and that's really the fundamental issue of, with quantum mechanics and measurement, when you can say it is like this object has spin up or spin down, that is the nature of the measurement we've made. It's only at that point that that you get that loss of information. And so when does that point come? When, where is that question of irreversibility? But I remembered also what I wanted to say, because there is there's another aspect to it that is about the whole notion of emergent properties generally. And this is the thing that I don't know if I have really formulated it clearly in my own mind, but there's something that doesn't quite seem right about the fact that, as I said to you previously, we can ask more questions than nature can give us answers to, because somehow that almost seems to suggest you would expect intuitively that there is a sort of fundamental substrate out there that is full of information, saturated with information, and at progressively larger scales, you get a coarse graining of it, and you kind of get access to less of that information. And somehow there's sort of less, accessible information at the higher levels than the lower. So that would seem to imply that actually you're never going to have a surfeit of questions you can ask. You're actually going to end up, asking a smaller subset of questions about the system than potentially you could ask. So how does it come to be that, in this emergent way, we find ourselves able to formulate more questions and think they are meaningful questions than they really are, because nature doesn't have the capacity to answer them. So there's a puzzle there, and I can't help suspecting that it's somehow connected to the puzzle of how we seem to acquire higher levels of agency than are apparent at the microscopic level.
That's so interesting. Okay, you got to please say more about that. We seem to acquire higher levels of agency at the more microscopic level.
Well, in the sense that I can move atoms in this, I can choose to move these atoms or not. Now, classically in the sort of, full deterministic picture, the answer would be, well, you're not, it's not, what is you even, making that choice. There are lots of microscopic interactions that are going on in your brain and around you, and that result in, this thing being moved. But we know full well that we will never find that agency that moves those atoms by no matter how closely we look. In fact, it disappears as we look at ever finer, grained levels of detail. There is no agency in there. So where does that come from? It then seems to be that the possibility of these atoms being moved isn't somehow inherent in the microscopic picture of it. So how do we understand where that agency arises?
Right. So would you? I mean, this is obviously it's at the borderlands between philosophy and science, but it's almost as if the mind is touching itself at that point, at that level of granularity, but only knowing that it's doing so because of the way that the atoms are forcing it to recognize itself. That it's the mind must recognize its own. This is what I thought, and maybe I said this, but and again, I know it's somewhat simplistic because it's sort of what you're stressing, but it does seem to be so fascinating that quantum mechanics essentially emerges out of this highly classical, which is very kind of Descartesian, Kantian, science is deterministic, universal, rational, and rationality, of course, it's rational, but rationality in science meant deterministic, right? The famous Laplace answer, I have no need of that hypothesis. And the faith that if you knew everything, all of the information, right, you could construct a completely deterministic, foreknowing, right, account of the entire universe, right? Laplace assumed that. And Kant, in a way, agreed in principle, even though he wouldn't have agreed at the level of human agency, and that's the problem for just interpreting whether Kant makes sense. But he agreed in science that in principle should be the case. But then, as you're saying, it seems as if, quantum mechanics forces, or, well, maybe it does force. I think the way that you're presenting it is very helpful in that sense. It forces a confrontation, which Bohr, and I think you bring this out very well. You show the kind of a very respectful way of showing why maybe people aren't as happy with the Copenhagen interpretation, especially now, but also why Bohr is fundamentally deep. And even where he's maybe confusing, it's because he's deep. It's because he really was puzzled in a way that only a great scientist can be, at the level of what he had himself sort of contributed to. And the puzzle does seem to be, as Heisenberg brings out, is that we're confronted with an image of our own agency when we now do science.
Well, certainly that seems to be the case in quantum mechanics. Yeah, that we have some choice about. John Wheeler said it this way, and if he hadn't have said it, I would have been too nervous to say it. But if he can say it, then I can. That we have some choice about the world that we bring into being. He talked about the participatory universe, and it sounds very, it sounds mystical, and if you sort of take it, at a superficial level, but it seems hard to avoid that conclusion when we recognize the contextuality of quantum mechanics, that we choose to measure this way, the system this way or that, and we get different answers, and we know we are going to get different answers, and there is no reason for us to suppose that those answers the one will be any less valid than the other. They're aspects of reality, but we've chosen which of them is going to become an aspect of reality. And I think, it seems to me that it's very hard not to talk about it in those terms. So maybe we do have to accept that. We do have to accept that there is that sort of participatory nature.
Well, no, go ahead. It's very beautiful. And I wondered, this is another connection to phenomenology, not so much physics, but I wonder what you think of this. I don't know if you're familiar with the I think Husserl coined the term, but then Merleau-Ponty and others really developed it, the idea of the life world, the Lebenswelt. And one of the reasons that there's a kind of nerdy debate, I think, whether Husserl in this way was influenced by Heidegger, but either way, it's part of the phenomenological tradition that Husserl's use of the life world with respect to the role of the natural sciences, which of course he was a deep devotee of as a mathematician, and he wanted phenomenology to be eine strenge Wissenschaft, a rigorous science. He said that the fact is, though, that the life world is where the natural sciences emerge out of or into, right? That, in other words, the human world of meaning that already exists is the world that brings into existence everything that we call science. And science prior to quantum mechanics was capable of entertaining a philosophical, this is now me, but I think he has his own rationalistic version of this. Science, but other phenomenologists do not follow him, so I don't want to now claim this is not the phenomenology part of my development. Of just to your point here, the life world's fundamentality is the Husserlian phenomenological point, that the life world is semantically fundamental. That, in other words, it is the world of meaning, and to pretend that just because when we do science, just because science enables us this momentary abstraction from the fullness of our meaning structure, doesn't mean it's more fundamental. But a philosophical interpretation of science, you could say, has emerged, right? That's part of science itself, the sort of 18th century inheritance. Like I mentioned, this Newtonian sort of synthesis through the Enlightenment, which Newton himself might not have agreed with, but it's deterministic, it's causal in a way that we think is clear, right? Causality is just this sort of unidirectional thing, and in principle, therefore, because the universe isn't quantum in the classical picture, that there's no reason things can't just sort of slide back and forth if you fully understand them. So at any one point, you could, and then as you said yourself, that would seem to eliminate human freedom or human agency, in the sense that it would eliminate an object's pastness in a similar way if you thought you could still add stuff to it. So somehow something has to be closed off, but what closes things off seems to be us. And so from the standpoint of the phenomenological use of the life world as a kind of phenomenological philosophy of science, what I think is profound is when you're doing natural science or natural philosophy, it seems like we used to think, well, we can ignore or pretend that the life world doesn't exist, that we are not the ones who fundamentally have spent billions and billions of dollars and done this enormous world historical thing that was connected to these highly contingent events, like, say, why do we have the Los Alamos Laboratory, right? Or all the war, all the stuff that makes science possible in the way that we're now doing it with the colliders, this highly expensive, massively complicated, it's a human thing that doesn't make it not scientific. But this to me is maybe even connected to, I was thinking about your piece, that but at the level of quantum mechanics, part of the nature of it as a theory about forcing us to confront what role our own questions and agency has in the level of information or the quality of information we can get when we're studying systems at this extremely granular level, it implicates, once again, the life world in the actual most fundamental level of physics itself. And so, in other words, from this interpretation, it's as if you go within the life world into the most narrow abstraction where you can really pretend nothing else exists except physics, which people really we thought that for, maybe 200 or 300 years, it was possible to think that. But now it seems like at the deepest level of physics, the view that you just mentioned, the beautiful sort of the world is participatory, which Whitehead would have found very congenial, as well as the phenomenologists, it's almost as if the science itself is pointing back that way. Again, that's a particular interpretation, but you mentioned the phenomenologists. I don't know what you make of that, the use of the life world.
Well, yeah. I mean, I know, that literature a little. I can't claim to know a lot about it, but what it was making me think about was, I mentioned this question of when we can say something is real, when we can say something happened, when we can say this was the outcome. And I suppose it occurs to me that actually that is something that is an issue. It's an issue for us because that's it's not, the objects around me aren't confronted with that problem of being able to say that, what is the past, when does something really happen. This whole question of at what stage does all the sort of potential outcomes that are out there in the decohering universe, when do they actually become, well, no, actually now it's this one thing and not that. And and when I think about it, I think that is actually a problem for us. That in principle, if the universe, was happy to just go on decohering, and somehow if some great force could come along that could recohere it, at any moment, fine. That's what quantum mechanics sort of that's the universe quantum mechanics gives us, this one that always, is decohering, but has the potential to recohere in principle. It's only us that has to say, no, at some point we have to be able to say, this has happened, it can't be undone. We don't know when that point is, we have no description of that point, and we can even create experimental situations where that point is not well defined, so that it looks as though we can somehow undo things that have already been in the past. So the world seems to be saying to us, that's fine, that kind of world, but it's not fine with us, because we have this sense that, come on, at some point you say this happened. So yeah, I kind of, I wonder whether that's in a sense, what you're getting at, that's also the sort of irreducible role that we seem to have in needing to insist on this distinction between, the past and the present.
Fascinating. Yeah, I think what that then brought to my mind is, I think about this a lot in epistemology, which is, right, we forget that everything legal is a fiction in a very technical sense, right? In other words, imagine you're a lawyer, and it's the same thing in science, and someone says, someone has a witness and they say something harmful to my case, and I'm the lawyer and I say, I make a motion, this is a US law, I don't know if they could be in the UK, but I make a motion to strike that as evidence, and the judge agrees. So what happens? Well, a witness said something, but it's not legal. It doesn't exist in the court.
Yeah.
Why? Because the judge said so. The judge, when did it not exist? When the judge said so, which was definitionally after the fact and resolved to a deliberative impulse, which is a member of the court motioned for consideration of its non-existence, and it'll let it be struck from the record. And then a judge issues a sentence, an ortile, a judgment, right? Which is a constant critique is the doctrine of judgment. And the judgment is what constitutes the legal event, right? So it's like, if you ask, why isn't it part of the record? It would be, well, because someone decided. But the person who decided why it wasn't part of the record is the same person who literally constituted what counts as the legal record of that case. That the judge and the court being in session, and the session following the proper protocols. And so once you get a court system where you have to try cases that implicate the rules and norms of the court, then it seems like we're in quantum mechanics.
Well, that's such an interesting way to think about it, because it's returning me to, this question that I think is the absolutely right way to talk about it, of what we are permitted to say and what we are not permitted to say. And I think, that it seems to me to be the right language to talk about quantum mechanics, and it's a really peculiar language for science. But I think that it seems to be what we're forced towards. So that, that too is kind of legalistic.
Right. It's as if the data and the science is giving us like norms and constraints that we have to operate as like lawyers, or else we don't count as doing what we thought we were doing. If we don't follow those rules, it's not scientific anymore, because we know we're not obeying what we've already learned about nature.
Yeah.
But then the weird thing is, nature is saying, you're doing something to me, which you have to take account of.
Well, and you see, what's really interesting to me too is that those constraints, those almost legalistic constraints that quantum mechanics and nature seems to give us, are also constraints about information. That you can formulate them completely. I talked about reconstructions, I think, last time we spoke, and the axioms are formulated in informational terms. One of them being that you are forbidden to make an exact copy of an unknown quantum state, unknown in the sense that the information in it hasn't been determined. And in principle, you can imagine doing it. You have a spin that you haven't measured, so it could be up or down. There might be a way of, projecting that into an exact copy of that same system. But quantum mechanics says, no, you can't do that with that. No, that's an informationally forbidden process. So, yeah, I guess that seems kind of relevant as well to this sort
of. And I wish this is something that I meant to bring up, but maybe some other time we can just chat about it, because that I thought was so fundamentally fascinating and interesting about the non-cloning principle, and connected even to honestly big debates about the architecture of the internet, right? Some of the original architects didn't want copying. It's extremely interesting that kind of principle, that you cannot make at that level, you cannot make a copy. And as you point out, that has huge implications, like even practical problems in constructing quantum computers. But yeah,
cryptography, that is the whole basis of, the security of the quantum internet. The fact that you can't make those copies. I mean, it's really striking that that's what it rests on. Yeah. Yeah,
it's telling, but I don't want to keep you. And thanks so much, Phil, for your time. It's great to see you, and thank you again for such an extraordinary book. And
thanks so much for your interest. It's great to talk.
All right.